now that I'm recording. Dang it. Um, okay. Now, what we've been dealing with up to this point are what are called direct methods for solving Ax equals b, Gaussian elimination and its variants like Cholesky decomposition, etc. So now we're going to look at a whole other category of iterative methods, at least take a very brief look. I get more in-depth into this in the purely graduate numerical linear algebra course, which is Math 610, offered every other spring. So now that we've spent a lot of time on Gaussian elimination, I'm going to talk about all the bad things about them. There are several reasons. Now, in certain cases, they're still a good idea, but there are multiple reasons to consider another approach. Okay, and in fact, I have, I believe, 4 reasons lined up. Okay, so the first reason is so elimination methods for, whoops, not there, for Ax equal b. Okay. What if we already know of some ballpark, something in the ballpark from a solution X? And I'll give an example of where that would come about. That's something we'll get into later in the semester. Implicit time-stepping methods for systems of ordinary differential equations. So you compute a solution at a certain time, like Tn, and you want a solution at time Tn plus 1. Well, to advance from time n to time n plus 1, you'd solve an Ax equals b problem. And because the solution is only changing over a small time step, whatever delta t is, the solution at time n already is a good approximation of a solution at time n plus 1. So you have an approximate solution in hand already. So Gaussian elimination has no way of taking advantage of this knowledge. So Ax equals b, or elimination methods, they take A as input, B as input, and just work with that to turn out a solution. There's no mechanism for using any outside knowledge that you have about the solution. And the thing is, sometimes we actually have that information. We'd like to be able to use it. Okay. The second issue with elimination methods is in many cases, in many applications, trying to get a highly accurate solution to whatever mathematical problem is really not practical. For example, suppose you're solving Ax equals b, but A and B, your input to the problem, already have a lot of uncertainty in them. Like maybe they come from measurements and those measurements are off. So if there's like 1% error, let's say, in A and B, and then you solve X equals B, then X inherently is off to some degree. But if you're solving that problem exactly, if it's a highly accurate solution, it'd be nice if you could do less work and get a solution, and then you're settling for a solution that's less accurate, but the error of that solution is error that you have anyway, that there's no getting around. So elimination methods has no way of quitting early in exchange for less accuracy. So if you already have a certain, if you already know you get a certain amount of error, that's well above a round-off error you would get from elimination, it'd be nice to do less work. But Gauss elimination doesn't work that way. Gauss elimination has no point at which you can jump off. You have to see it all the way through to the end to have any solution at all. Now that solution will be quite accurate, aside from rounding error and so forth. So that amount of work may be seen as excessive. There are a lot of applications where having 1% error, let's say, is perfectly fine. Okay, so we'd like to be able to stop early if the application calls for it. Okay, this one has actually already come up. What if the matrix A is sparse? In other words, most of the entries are 0. So elimination, and what we've talked about in particular is pivoting, could lead to fill-in. Now, so where we've talked about this already is with a banded matrix. Now, a banded matrix is sparse, and if you don't pivot, then L and U will also be sparse. But if you pivot, you might get fill-in. Fill-in is a problem beyond just banded matrices. So if you have a matrix that is sparse, and maybe the non-zero entries are like more randomly scattered, like if they're not in a band, and then even without pivoting, just doing elimination, like so subtracting a multiple of one row from another row, those elimination operations could also lead to fill-in. So it'd be nice to have another approach to AX equals B that would not destroy the sparsity of a problem. Okay. And finally, what if we don't even have a matrix A? And what I mean by that is you don't have it explicitly as a two-dimensional array where you have each entry Aij. So what would be an alternative? Because you think, oh, don't you absolutely have to have A? Well, not really. Instead, we have a function A of x that returns the matrix vector product A times x. So in other words, this function is kind of a black box that carries out matrix vector multiplication. Now, if you have such a function, you certainly can get A by passing all the columns of identity for x. So you return A column by column. But you don't want to have to go through that. So it'd be nice if we have methods that do not require an explicit representation of A. So certain iterative methods will accommodate that. So for cases where direct methods are perfectly fine, and I've referred to as elimination methods, but when I say direct methods, I mean Gauss elimination and its variants. But for a given AX equals B problem, it's worthwhile to consider whether an iterative method might be more practical based on your particular application. Now, in this class, we're only going to see one class, or category of iterative methods. Those are called stationary iterative methods. So there are other kinds that are very different, and those will be covered in Math 610 if you ever take that. Okay. Now, so what do I mean by stationary iterative method? A stationary iterative method, again, for AX equals B. Stop that. Is a method of this form where each new now. So the way I'm going to represent iterates is using a superscript with parentheses, so as not to get confused with an exponent. So we start with some initial guess, x0. Okay, and the idea is you substitute x0 into this function g, and you get x1. You substitute x1, you get x2. Substitute x2, you get x3. So you keep substituting into g again and again and again. And the idea is, hopefully, this iteration will converge at some point. So the xk's will converge, and then what they converge to is the solution of ax equals b. So this is based on what's called fixed point iteration for solving an equation of this form, x equals g of x. Okay. Now, later on in the semester, we're going to talk about root finding methods, like Newton's method and so forth. And those are based on fixed point iterations. So if you can take any equation at all and describe it in this form, which is always possible to do, just for algebraic manipulation. There's a lot of theory about iterations for solving an equation like this. So the solution, if it converges, the solution x is called a fixed point, also called a stationary point. So that's where stationary iterative methods get their name. Okay. Now, okay. So, how do we build an iteration of this form for solving ax equals b? Okay. What we do is we take a matrix A and we write it as a difference of two matrices, m minus n. So the idea is you can choose m, and then this equation would determine n. So there's a lot of choice here, many different possible splittings. Okay. Then, from our equation ax equals b, which would be the same as m minus n x is equal to b, then I could write the following. Mx is equal to nx plus b. So I'm just moving the n term to the other side. So now I can obtain this iteration. M x k plus 1 is equal to n x k plus b. Okay. So the idea is, given the initial guess x0, I can plug it in here, and now I have a system to solve with m instead of a. And I can choose m to make sure that that system is easy to solve, like maybe making m a diagonal matrix or a triangular matrix. So this is a fixed point iteration of a form I have up here with my iteration function g being defined this way. M inverse nx plus b. Okay. So if I multiply both sides by m inverse, I have xk plus 1 isolated on the left, just like I have up here. So whatever is being done to xk on the right, that's your function g. So now I have this fixed point iteration defined. Now I'll discuss certain choices of m in a little bit that lead to well-established iterative methods. But before that, I want to talk about, for a general case of any kind of splitting like this, how do we know whether this iteration will converge? All right. So we want to make sure that the error goes to 0. So if I look at these equations, so I'm going to take and since we have it right in front of us, I'm going to take this equation and subtract it from this one. So on the left side, I'm going to have m xk plus 1 minus x. Now, the nice thing is, x is the exact solution. This is our approximate solution. This is the error after k plus 1 iterations. So then I subtract the rest of this. Well, the b's are going to cancel. So I'm going to have n times xk minus the exact solution x. Okay. And then what I can do is I can multiply both sides by m inverse. So I'm going to stick an m inverse over here and get rid of it over here. Okay. So now what I can say is that the error after k plus 1 iterations is the error after k iterations times m inverse n. So m inverse n is potentially amplifying or maybe damping that error from one iteration to the next. We prefer that it damp it, like it makes the error smaller, because the error is supposed to be going to 0. So actually I'm going to move all of this onto a new page. Okay. Because this is what happens from one iteration to the next. Over k iterations, I have this situation. K m inverse n to the k times x0 minus x. So here, this is the error in your initial guess. So after all iterations, k iterations, this is the error that we have. So we're continually multiplying by m inverse n. Okay. So some terminology. I'm going to call this matrix m inverse n. I'm going to call it T. As called the iteration matrix. Okay. Now, so what I can do is I can take a norm of both sides, any norm. So it doesn't matter which one. They're all equivalent anyway. So I'll take this equation, okay, and I'll fill in norm on the left side, and then on the right side. Now, the norm of a product is less than or equal to the product of the norms. And that applies to this exponentiation also. I can say that this is less than or equal to this norm of m inverse n, and then the norm is raised to the k power. Now we want this error to go to 0. I mean, this, it just depends on how good our initial guess is. But we want this to be going to 0. So in order to guarantee that this error is going to 0 as k goes to infinity, so what has to be true about this iteration matrix? So this is our iteration matrix T. I'll fill that in here. Okay. So what should be true of T, or the norm of T, to make sure that this error goes to 0? Sorry, what?
The norm of T needs to go to 0.
Well, the norm of T would only be... Well, T is a fixed matrix. It doesn't change from iteration to iteration. Now, it cannot... the norm of T cannot itself go to 0 because it would be the 0 matrix. But we don't need that. Because what happens is we keep multiplying by this norm each iteration. So whatever error we have up front, actually I don't need these parentheses here. In order to make sure that this gets smaller as k increases, what should be true of norm of T? It should be less than 1, or certainly it should be small. So that way we at least make sure the error is not getting bigger. So we can require that the norm of T is less than 1. In whatever matrix norm, like infinity norm, 1 norm, etc. So this is sufficient, but not necessary. In other words, if a norm is less than 1, yes, the iteration will converge. It is possible that some norm may be greater than or equal to 1, and the iteration may still converge. So let's go for a weaker condition that is necessary and sufficient, is that this quantity, rho of T, the spectral radius of T is less than 1. Now I need to explain what is the spectral radius. So spectral radius is the... Alright. I'll type it out first, then I'll explain the notation. All right. Now, okay. So, lambda of T, that is a set of all eigenvalues of T. So we're taking the absolute value of the largest one. So if all of the eigenvalues of T are strictly less than 1, so not less than or equal to, strictly less than 1, then the iteration will converge, and that is required for the iteration to converge. So if the spectral radius is greater or equal to 1, convergence will not happen. Okay. Now, lambda is an eigenvalue if we have this relationship, Tx is equal to lambda x, for some non-zero vector x. Okay. All right, so this is a condition that we need to be satisfied. In some cases, it might be easier to show for a given method that the norm is less than 1. So it just depends on the method. So the idea is when you have the spectral radius less than 1, then as you keep multiplying a matrix with itself, and looking at the t to the k, t to the infinity, basically, that matrix is going to 0. Now, we can say that the spectral radius of t is less than or equal to t for any induced or natural, any matrix norm that's based on a vector norm that we have this relationship. So we can see why, like, this condition requiring this to be less than 1 is sufficient but not necessary. So if the norm is less than 1, certainly the spectral radius will be. But also why the condition is not necessary. And I can show you why. Because if you have an eigenvector and eigenvalue pair like this, tx equals lambda x, where that eigenvalue, it gives you the spectral radius, in other words, its magnitude is equal to the spectral radius, then we have the following, that okay. So if I have this equation, lambda x is equal to tx, and then what I do is I take the norm of both sides. Okay. Then lambda is a scalar, so I can pull it out of the norm as long as I take the absolute value. Then lambda is magnitude of lambda is the spectral radius. But over here, tx, the norm of a product is less than or equal to the product of the norms. So then I can divide both sides by the norm of x, because x is non-zero. And then what do I have? Spectral radius of t is less than or equal to the norm of t. Okay. And I need to emphasize where, stop that. Where x is not equal to 0. Okay. All right. So that's when we know an iteration converges. Now what I'm going to do is show some specific choices of splittings m into a equals m minus n that lead to certain methods. Okay. I need some more notation to do that. So I can let A equal L plus D plus U, where D is the diagonal part of A, so only consisting of the diagonal entries. L is the strictly lower triangular part, and U is the strictly upper triangular part. Now, this has nothing to do whatsoever with the LU decomposition. So I need the flexibility to use L and U, letters L and U for other things. All we're saying is, take the entries that are below the diagonal, strictly below, you put them in L. Everything strictly above the diagonal, put into U. The diagonal entries go into D. So it's just a notational device to break up a matrix into these three key parts. Okay. So now that makes it possible for me to describe these iterative methods. So the Jacobi method comes from setting m equal to d, and therefore n is equal to minus L plus U. Now, if we look back at the general iterative method, stationary iterative method, we have this. We have to solve systems involving M. And I'll make a note up here. To be practical, systems involving M must be easy to solve. Like if M is diagonal or triangular, then that will work. Because you want to make sure you're expending a lot less effort than solving systems involving A. Because for these, it's most likely to use a direct method. Okay. Now, all right, so the Jacobi method, that certainly works. We can set M equal to a diagonal matrix. So that system, certainly can be solved. Okay. So now here's what the iteration looks like. X k plus 1 is equal to D inverse. And then I have B minus L plus U x k. So this describes our iteration. So we make an initial guess x naught, whatever. And if you don't know how to pick initial guess, you can always choose x naught to be the 0 vector. So then you'll substitute that in here and just grind it out to get x1, and then substitute x1 in here to get x2, etc. Now, D inverse is trivial because D is a diagonal matrix, so D inverse is also diagonal, and you're just taking 1 over the diagonal entries of A. So in other words, you must have all non-zero diagonal entries, or this method won't work. If you don't have that, maybe some row operations, like row interchanges, would fix that. Okay. So now what I'm going to do is use this formula to describe how you would get the entries of xk plus 1 on a component-by-component basis. So if I take each component of both sides, so I'd have, on the left side, I'd have xi k plus 1. Now, on the right side, I have component I of this vector. And I'm dividing by the diagonal entries of D, which also are the diagonal entries of A. So it's diagonal entry number I. In other words, I'm dividing by AII. Now, in here, I have the ith component of this vector, so I'd have BI. And then I'm doing a matrix vector product. Aij x j iterate k. Except for one thing, I'm not including the diagonal. So this is slightly wrong. So what I'm going to do is I'm going to include a condition j not equal to I. Okay. Okay. Now, so this is a way. So this is closer to how you might code up the Jacobi method. So you would have a loop. So this is done for all I, 1 to up to n. So during each. So what you could do is in your code for the Jacobi method, if you're writing and this does come up on the next homework, or I think it's homework 4 really. You'll have a loop that controls the iteration. And in that loop, you're computing xk plus 1. To compute xk plus 1, you'll have an inner loop, like I going from 1 to n. That will compute each of these components. And here's a formula that you would implement. Okay. Okay. So So the implementation, you're given the initial guess. And like I said, if you don't have an iterative initial guess in mind, you can always just use the zero vector. Have an outer loop for computing each new iterate, xk, or xk plus 1 really, from xk until some stopping criteria is met. Now, there's a lot of choice as to what you would stopping criteria you would use. So I'll just give an example. Like you could examine the norm of the difference between successive iterates. So you can set some tolerance. Like maybe 10 to the minus 5 or something like that. And you can use whatever norm you like like a 1 norm or 2 norm or infinity norm. Because as the iterations are converging, this difference is supposed to be going to 0. So you can keep this outer loop going until this condition is satisfied. Like it could be a while loop, for instance. But for practical implementation, use a maximum number of iterations, like 200 or something like that. Okay. Something to keep in mind when coding up iterative methods like this one. Okay. Now, I'm going to take this formula for the Jacobi method put it down here, but I'm going to write it a little differently. Here I have this sum over all j not equal to I. So I'm going to break it up into two sums. First sum is for j less than I. And the second sum is for j strictly greater than I. Okay. Now, if we assume that we're computing all of these components of a new x in order, so first component, second component, etc., then what's happening here is, like, suppose I'm looking at component number 4. So x4, k plus 1. In this summation right here, I'm using x1, iterate k, x2, iterate k, and x3, iterate k. The thing is, though, I've already computed x1, x2, x3 of iterate k plus 1 from when I use this formula for I less than 4. I have information about the new solution, and I'm not using it. So this formula uses old information for xj k. So actually, that is the old information when j is less than I. So what I could do is I could modify this. Okay. So all I'm going to do is change this first summation to use k plus 1. Because when j is less than I, this element of xk plus 1 has already been computed. so I might as well use it. So this is the Gauss-Seidel method. Now, if I want to describe it in the same kind of matrix form that I have here for Jacobi, I have x k plus 1 from the left side here, and that is equal to okay. I want to make sure I am getting this right. So I have D inverse still on the left side. And then in these square brackets, I still have B. And then I have minus. Now here, these are entries Aij, where I is greater than J. That's the lower triangle. So that's going to be L x k plus 1. And then here, I have J greater than I over here. That's the upper triangle. So that's U x k. All right. So now what I'm going to do is rearrange this. I'm going to take the D inverse out of here. I'm basically multiplying both sides on the left by D. So now I have a D over here. Okay. So now I'm going to move this term, Lxk plus 1, to the other side. So that would be the same as D plus L. And now this term is gone. Okay. And finally, I can multiply both sides by D plus L inverse. Okay. So now I have it in a similar form as I did for the Jacobi method. So in other words, in terms of a splitting, M is equal to D plus L, and N is equal to minus U. All right. Now, here's the strange part. In Jacobi, the system I've solved with M is a diagonal matrix. With Gauss-Seidel method, I'm solving a system involving triangular matrix. It's a forward substitution. And you might think, well, diagonal system involves n flops. Triangular system involves order n squared flops. And yet, it should be pretty obvious from looking at these two side by side. The amount of work involved is pretty much exactly the same. Well, it literally is exactly the same each iteration, because we're just pulling information from different parts. But in terms of actual amount of computation, the amount of work involved is no different. And why is that not a contradiction? Well, for one thing, with Gauss-Seidel, we're doing less work in forming the right-hand side. The work is cut in half, because we're only multiplying by U, not also L. The work involved in multiplying by L in a Jacobi method is shifted to the part where we're solving a system for forward substitution. So we're just moving some operations around. Because keep in mind, what happens here for both methods, like this uxk down here, or L plus U times xk, that's a matrix vector product. That's order n squared flops, just like forward substitution is order n squared flops. So we're just moving operations from moving individual arithmetic operations from one matrix operation to another. So that's why there's really no contradiction here. Okay. In some cases, it can be proven that Gauss-Seidel converges more rapidly than Jacobi. As a consequence of using more up-to-date information about the solution. It's not always true, but certain key applications it is. A disadvantage, though, Jacobi can be parallelized, whereas Gauss-Seidel cannot. So if we look at Jacobi, the fact that we're here, we can compute these components of xk plus 1 in any order. And we can do it simultaneously because all the components are using old information about xk. Whereas this formula is only correct if we actually do compute the components in sequence, I going from 1 to n, in order to take advantage of making sure this new information is actually available. But because we're locked into a particular order, that means that we lose the option of parallelizing. So there's no clear winner here, because parallel architectures are a lot more important now and growing in importance. Because we kind of hit the limit of what we could do with just a serial computing. Okay, so there's something to keep in mind in terms of choosing. Like, you might think, oh, who needs Jacobi if we can update it and get Gauss-Seidel? But Jacobi is still used, and largely for this reason. Okay. Now, there's one important variant of Gauss-Seidel. Okay. And that's called successive over relaxation. So I'm going to take the formula for Gauss-Seidel. Okay. And I'm going to add onto the right side xik, and to compensate, I'm going to subtract it, of course, but in here. Okay. So this part right here, everything starting from 1 over AI all the way to the end, you can think of it as the step that we're taking from iterate k to iterate k plus 1. So this is the actual change in the solution. So what if, as we're converging to the exact solution x, if we like to take a larger step in this direction than what Gauss-Seidel would do? So what I'll do here is, okay. Need to make sure that what I have written here is actually right. Okay. D plus omega L. Okay. Okay. So in direction of x, I'll just play my notation in a moment here. So xk plus 1 gs, that's what Gauss-Seidel would give us. And then this is just our previous iterate. So we would like to go further in this direction, perhaps, because that might get us to the solution more rapidly. So we introduce a relaxation parameter that I'll call omega. So all that means is I'm going to take this formula right here, and I'll put an omega right there. Okay. Now, because the thing is, what's very important, if we look at what's in here, let's suppose that the xk's have converged, presumably to the exact solution x. What do I have here? B, and then all these are add up to minus a times x. Here's the lower triangular part, the upper triangular part, the diagonal part. So this is b minus ax, which is supposed to be 0. So if ax equals b, then this will be 0, and xk equals xk plus 1, which is what you'd expect from convergence. So we're still solving the same system, ax equals b. I'm just introducing this parameter omega. So now what I'm going to do is I'm going to do some rearranging here. Okay. All right, so copy the same formula. And I'm going to multiply both sides by AII. Okay. And then over here I have, this also needs AII. Okay. And notice I have this term here and here, but this one's multiplied by omega. So I'm going to have 1 minus omega. So now I can remove it from here. Okay. Now, okay. So now I have, on the left side, I have d x k plus 1. Here I have 1 minus omega d xk plus omega, and inside the square brackets I have b minus l x k plus 1 minus u x k. And okay, so now if I do some rearranging with this, I want to move this term involving xk plus 1 over here. So it's really d plus omega l xk plus 1. So now I can remove it from here. Okay, and then I can take everything involving xk and put that together. So 1 minus omega d minus u times xk plus omega b. All right. So this method, which in the case of omega equals 1, is just Gauss-Seidel all over again. But for general omega, this is the successive over-relaxation, or SOR. Okay. So it's a more flexible version of Gauss-Seidel with its relaxation parameter omega. So convergence requires that omega be strictly between 0 and 2. And that's explained why in the... oh, actually... Did I just give away a homework problem? Well, not entirely, but let me check. 5.1... Oh, I did not assign that one. Okay. All right. So, so I'll quickly show why, since you don't have to for homework. So the iteration matrix for SOR, I'll call it T omega to indicate it depends on omega. So that'd be D plus omega L inverse. Really, it's whatever's multiplying xk, keep in mind that I multiply by the inverse of this on both sides. So it's this inverse times all that. Okay, so let me just grab that. Okay. All right, so that's the iteration matrix. If I take the determinant of this matrix, well, so what we have here is determinant of a product is a product of determinants. The determinant of the inverse is a reciprocal of a determinant. Because this is a lower triangular matrix. Its determinant is a product of the diagonal entries. But now I have the reciprocals. So that gives you the determinant of this part. Then over here, only the diagonal matters. So now I have 1 minus omega times AII. But these AIIs cancel with these. So it's just 1 minus omega to the n. And we have to have determinant is a product of all the eigenvalues. So we keep in mind that there's a product of all of them. Then the largest one so that's a product of all the eigenvalues. And that would mean that the spectral radius, which comes from the largest of these, must be greater than or equal to absolute value of 1 minus omega. So to ensure that this expression is strictly less than 1, omega must be between 0 and 2. Most applications, it's better to choose omega to be between 1 and 2 that's what leads to over-relaxation. So you can think of omega between 0 and 1 as being like under-relaxation. Okay. Choosing the right omega, the best omega, like the speed of convergence, is difficult. Over certain problems, it is known how to choose it optimally. Okay. I should mention about SOR. It was actually developed by a PhD student way back in 1950. It's introduced by David Young. Dissertation, 1950. So you could actually look this up. So it actually, I think people have, I guess back then dissertations were typed on an actual typewriter, the old-fashioned kind, because that's all there was. But I think someone has put out a modern and therefore more easily readable version of it. Although I think I found a mistake in it. The method definitely works, but there's a lot of proofs about it and so forth. But I saw one thing in there. It's like, I don't know. But this is definitely the kind of thing that makes every graduate student feel like an underachiever, because not many get to invent SOR or something of that magnitude for their dissertation. Then again, there are a lot more opportunities to invent great things back in 1950. So much has been taken up now. Okay. Well, there's only 5 minutes left in regular class time, so what I will do is I will stop here, and then anyone, of course, who has any questions about anything about the test or about homework, and you're welcome to ask now for everybody's benefit, or you can just ask me individually. So whatever you want to do.
You want to test
Yeah.
number 8 question? I was not quite sure.
Number 8?
Yeah, on the test on the lightning.
Okay.
So the answer has been that we're emitting 1 entry per column and 1 entry per row.
Well, okay. So what I was really looking for is how the amount of work you need to do changes. Like there's only one element to eliminate per column, and each row operation only affects one element. So that's why you end up, and then so therefore there's only n row operations, or n minus 1 really, each doing a small amount of work, and that's why it goes from n cubed all the way down to n.
Yeah, but I was thinking like if I had using this integration and choose 1.
Okay.
Like, convey the same idea.
Okay. Well, I can look at it again, but yeah.
Yeah, because I thought of it like writing, say, we are emitting 1 entry per row, 1 entry per column.
Right.
And so it simplifies to just n. But I was thinking in a more general sense, since we've already said it's for the MPQ and P and Q.
Yeah, I think I might have been looking for something as to, what is about the work involved that leads to it being NPQ in the first place, and therefore, and then because P and Q are 1, okay. I know it's kind of splitting hairs, but I can reconsider.
Doesn't matter.
Okay, I know. Okay. Other questions? Okay, well, I'll stick around if anybody has any. So.